So we're going to do let me see. We'll do the electrophilic addition one right here. So we're going to do this example. So electrophilic addition of Hx, where X is a halogen. So it can be HCl, it can be HBr, HI. HF doesn't really, it's not that good of an electrophile. So or most of the times you'll see it done with either chlorine, bromine, or iodine, right? So I have it already drawn, so I'm going to cheat right here. So this is the actual alkene drawn out that I have shown right here, right? And so this, in the mechanism, whenever you add Hx, all of these are addition reactions, and then your alkene is always going to act as your nucleophile. Right, so these are addition reactions. Anytime you start with a pi bond as your starting material, it's going to be an addition, right? When we talked about the different types of reactions, elimination, substitution, addition, and rearrangement, addition always started with a pi bond, and then elimination always ended with a pi bond, all right, in the product. So the first step in the mechanism is attack of your alkene or your pi bond on Hx. Right, so the electrons in that pi bond are used to attack the proton here in HCl. And then you also, by the same token, break the HCl bond, right? So that leaves chlorine with a negative charge, which I have it shown somewhere else. I'm gonna put it up in a second. But in all of these reactions, your alkene is acting as your nucleophile. And in this particular reaction, it's stepwise, and it goes through a carbocation, right? The carbocation in this reaction, which I have shown in purple in brackets, that carbocation is always going to end up on the most substituted carbon. All right, it's not going to end up on this side, because that will be the equivalent of putting it on a secondary carbon, where when you have a choice of putting it on a tertiary carbon. So the carbocation that you see right here is a tertiary. And if you remember the rules for carbocation stability, right? We said that a tertiary was the most stable. That's what this is here, but I'll just rewrite it. So you have tertiary, which is more stable than secondary. Stop spying on me, Bixby. My phone is all of a sudden just recording. I did not ask you to find nothing online. Right, so tertiary is a better carbocation than a secondary, which is a better carbocation than primary, which is better than methyl. Tertiary is the best, methyl is the worst, right? So your intermediate is always going to end up on the in the location where it's more stable. Any questions so far? And this is, again, that reaction where we take Hx and add it to an alkene. Always goes through a carbocation intermediate. Right, so your carbocation here, that's what is going to be attacked by chlorine, the chlorine that left. Right, if you look up here, the arrow goes from the pi bond to hydrogen, and then you break the HCl bond. So the chlorine that left now is going to attack your carbocation. right? And so the chlorine ends up at that position, right? Or in that region. So once the chlorine attacks, you end up with your product. You can see that for this particular reaction, where you add HX to a double bond, the chlorine ends up on the more substituted carbon, right? That regiochemistry is based on what we call Markovnikov's rule. Hold up, let me zoom in so I can make that a little neater. Based on Markovnikov's rule. What that rule says is that for in this particular reaction, the halogen is going to add to the more substituted carbon. How do we tell if something is more substituted? What does that mean? Don't be scared to speak up. It's Wednesday. When and when.
It's like the trisubstitute, disubstitute, monosubstitute, and all that.
Or what? Tertiary, secondary, primary. That's in this case it will be that, because disubstituted is referring to the actual alkene, right? But you can predict where the halogen will go if you look at the alkene and say, well, this side is trisubstituted and the other side is disubstituted, so it's going here. You can use that to predict the outcome of the reaction. But based on Markovnikov's rule, a more stable carbocation is where your is going to predominate, and that's where your chlorine is going to end up. Your halogen is going to end up. All right. Any questions about that? So Markovnikov's rule tells us about what we call regiochemistry, right? You got two sites, two reactive sites that are possible. And so the regiochemistry is going to be dictated by stability. Which site is going to be more apt to be a carbocation, right? That's the concept of regiochemistry in a nutshell. You got two sites that are possible, two places where a reaction can take place. And so the reaction is going to take place, in this case, at the more substituted carbon. All right, any questions about that HX addition? About the mechanism, about the carbocation, about anything? All right, let me add a page. And then we're going to look at a different reaction. We looked at halogenation on when we met on Monday night, but I'm gonna take the halohydrin because they're very similar. So we'll take this reaction right here. How many of you have started making flashcards? Anybody?
Yes.
One person.
Yes, I have.
Two people. All right, praise the Lord. That's about, let me see. We got 24 people here. That's 1/12. That's about 8% of the class. I promise you, this section, it can whoop you, or it can make you a better student. It's up to you. If you want to be a better student, make the flashcards, write the details of the reaction on the back, and write the reaction itself on the front, so you can get a handle on all of this material. It's a lot of material, right? So this reaction that's shown here is an example of what we call halohydrin synthesis, right? A halohydrin is exactly what it sounds like. It's a halogen. It's basically, let me just write it down here. It's a halo alcohol, right? So you have a halogen and an alcohol functional group in the same molecule, right? So that's what a halohydrin is. Look at the reagents, Br2 and then water, right? So let me show you the product, then we're gonna go through how it works, we make it, how we get to it, right? So here's the product. The product is gonna look like this, where the 5-member ring is here, still intact. We don't touch anything on that ring, because none of those carbons are reactive. I want you to keep in mind too, we're talking about alkenes, so the only thing we care about is what happens at this double bond. We don't care about nothing else. So don't worry about the carbons on the other side. Don't worry about any other functional groups. All we care about is the alkene. Right, so I'm gonna show you the product. Uh-oh, not like that. That's the product. This is the halo part. This is the hydrogen part, because that OH actually came from water. Sorry about that. And we'll see what I mean by that when I say that the OH is derived from water, right? Any questions so far? So we got the halo part, we got the hydrogen part, and there's a couple of things, a couple of key points we're gonna make about this that you can put on the back side of your flashcard, because all these reactions have certain characteristics, right? All right, so let's look at let me see if I need to add a page or not. No, not yet. Let's look at the mechanism. What's a mechanism? Somebody tell me what the definition of that is. Anybody?
Is it like showing the transfer of electrons?
Yeah, it's a step-by-step depiction of how a reaction happens by showing how the electrons are moved from one molecule to the next. Yes, right? A mechanism is basically a map of how a reaction goes from point A to point B. Right, that's what we're showing. So in the mechanism, let me show you what happens. So the first thing that happens is what? Anybody? So this is Br2. If the alkene is my nucleophile, what do you think is going to happen when it sees Br2?
It's going to attack.
It's going to attack it. And again, let me go back. Oh, it's frozen. Come on, man. All right, let me go back to another idea that we talked about between nucleophiles and electrophiles, right? But the nucleophile is the source of your electrons. The electrophile is the sink. It's going to be your acceptor. It's accepting electrons. Every reaction we do, you can apply that principle of nucleophiles and electrophiles, right? We've learned basically two types of reactions, or two principles. We learned acid-base chemistry, and we've learned nucleophile electrophile chemistry, which both operate on the same principle. You have a source and a sink, right? You have something that's a source of electrons, and it's reacting with something that's an acceptor or a sink for electrons. All right, so the first step here is going to be nucleophilic attack. On bromine. So that's coming here, boom. And then what has to happen with the bromine-bromine bond? I got to break it. Is that right?
Yes.
Yeah.
All right. So now this is tricky. This is kind of a tricky part. I talked about it Monday, so I'm gonna kind of spend some time to make sure we understand it. So whenever you add a halogen to an alkene, it goes through this type of intermediate. It's called a Helonium Intermediate. So I'm gonna draw that down here, and I showed it on Monday night, and I'm just kind of recapping it because it's this reaction and halogenation go through the first step is identical for both of them, right? So here's the intermediate. I'm gonna bracket it in. I'm gonna put bromine here. I'm gonna put a plus charge there. And then outside the brackets, I'm gonna put the other bromine, which is negative. I don't know why there's a lag. All right. This doesn't stay like this. This actually collapses down where bromine will intramolecularly attack that carbocation. So that closes down and gives you this. So we're going to call that intra. Zoom in some. It's called an intramolecular. Intra meaning that is happening from within the molecule. If something else came in and attacked the plus charge, that would be what we call intermolecular. But because it's happening in the same molecule, it's intra. For that, what's your nucleophile?
The bromine.
Bromine. That's your source, right? And the carbocation is the sink. Now, this normally, you don't draw this like this, but I'd much rather you see how it closes up as opposed to just trying to be fancy and putting a 3-member ring and then you sitting there looking crazy like, what just happened, right? So when the double bond attacks bromine, like we see up top, you breaking that carbon-carbon double bond. So this carbon right here is going to become electron deficient. That's why I put a plus charge there. And then bromine is going to come in, boom, and attack that plus charge. So you get this 3-membered ring, which we call, again, this is, wrong pen, sorry. It's a bromonium ion, right? Everybody okay with that? Anybody like freaking out? If you freaking out, say something. We can make it better, I think.
I have a question.
Go ahead.
What does the intramolecular mean again?
It means it's internal. Like,
Okay.
let me show you an example. I gotta add a page anyway. Let me see. So let's say you had oh, come on. All right. Let's say you had a carbocation. Let me see. Let's say you had a carbocation here, right? And then, I'm gonna put a heading up here too. Right? So intramolecular, if you had a cation like this and oxygen attacked it and closed up and you made let me see, 1, 2, 3, 4, 5. You made a 5-member ring like that. Let me put this CH3 here so you can see what happened. You see how oxygen attacked that plus charge and then you end up with this ring closed up, right? This carbon right here is the same carbon that's right here. but that closure, it will happen in an intramolecular fashion because it was internal. Right, basically your nucleophile and electrophile are in the same place, and it will within the same molecule. So it'll be intramolecular. Does that make sense?
Yes, it does. Thank you.
And then if I had that same carbocation, let me cheat right quick. If I had the same carbocation and but instead of oxygen attacking it, let me see, crop that out. Instead of oxygen attacking it, I'm gonna just redraw it. That's sloppy and cheating. So I had the same carbocation, but I reacted it with, let's say, sulfur. Right, so this came in and attacked like that. That would be intermolecular. Right, so your nucleophile is external. It's coming from somewhere else. It's not coming from internally within the molecule. Following that, so then the product would be like this. Because your nucleophile was external and not internal. We're okay with that? So I'm going to add a page here. That way we keep some continuity. And I'm going to paste this down here. All right, so now we've added bromine. It's cyclized to give you this bromonium ion. And now we're halfway to the product. And I'm going to draw in a water molecule down here. All right. So with the water, now I can attack that ring with either bromine or water. Oh, never mind. Okay, I can attack with water or bromine. All right, so either one of those can attack that ring, but I want to point something out. If we go back up to the reaction, the original reaction scheme, right? You see how the water is underneath the arrow? A lot of times when you see a reaction written like that, the conditions under the arrow, or the conditions are listed under the arrow. So what we're saying here is that the water is the solvent. All right, so we're saying that the water is the medium in which you're carrying a reaction out. Right, so the way this happens, the water now can come in and attack that intermediate. So let me show that. Come in here. Boom, and then pop that ring open. All right. So what should I get from that? Think about it. The ring is no longer there, right? The water came in and popped that open. So I'm going to get this. Like that. Now water has a plus charge. And then the bromine is here, right? Plus, do you think that water is going to stay like that?
No.
Right? Because the end product is an alcohol, right? So the bromine ends up doing a quick proton transfer, right? And then we end up with our product. The product plus HBr. And the product is the halohydrogen. Right? So it's a long mechanism, but it's not that involved. It's just a lot of steps. Right? So that last step is a proton transfer. And then the step before that is attack of the water. Is water acting as a nucleophile here?
Yes.
It is, right? Water is your nucleophile. Okay, let me ask this question. I'm gonna ask a couple of questions. The first question is, I'm gonna ask 3 questions. First question is, why do you think water beats out bromine in attacking that intermediate? We're gonna answer all 3 of them. I'm gonna write them down here if I can. I got enough room.
Is it because
Come on, don't be scared.
I don't have the periodic table in front of me. Is it?
does it have to
I want you to think about what I told you about the solvent. Think about it in those terms. All right. Here's a let me put it to you in from a different perspective. All right. So let's say you got a fish tank, right? And in the fish tank, you drop in 1 piece of fish food. You following? Or you drop in
yes.
1,000,000 pieces of fish food. And there's 1 fish in there. All right, which scenario do you think the fish is going to eat the most? If we drop in 1 piece of fish food, or we drop in 1,000,000 pieces?
The 1,000,000 pieces.
1,000,000, right? That's common sense. So when we do this with water as the solvent, what we're saying is that there's so much water present as opposed to bromine that the water is going to win out in that competition. You following? So because you're running the reaction in water as the solvent. So for every 1 bromine that's present, you got 1 billion water molecules that are present. Let me put it like that. So the water is just going to be more available because there's more of it. So that's why you see water opening the ring up. And there may be some competition, don't get me wrong, but the predominant product is going to be the halohydrogen, right? So water beats out bromine because it's more plentiful. Does that make sense?
Yes, sir. Yes.
And water is a pretty decent nucleophile too. So don't forget that part. Even though, we don't normally think about water as a nucleophile, it's a very good nucleophile. And when you got that much of it, because you're running the reaction in water, then it's just much more, the concentration is so much higher than that of bromine till you see water acting as a nucleophile in this case. All right, here's the second question. What did I say? Let me look back at what I want to ask. So I asked about water. I asked about, oh, why do you think it opens at the site that you see? So I'm gonna call it so why is that carbon that's tertiary more reactive? Let me get my handwriting together first, and we'll go back up to that example. So let's look at the intermediate. You see the intermediate, right? Right here. You do, hopefully you can see that there are two possible sites for that water to attack. Is that right?
Are you referring to the like the carbocation and then the bromine ion at the top?
Yeah, yeah, I'm looking, I just highlighted those, the two places where water can hit in pink. Or is it frozen?
I see it. I'm sorry.
All right. So water can hit either one of those sites. Why do you think it chose the tertiary site? Think
It's
about
more stable.
that site. If you break the carbon bromine bond first, right? The carbocation that you get there is going to be tertiary. If you break the carbon bromine bond here on this side first, that's going to be a primary carbocation. So this site, the tertiary site, is more positive. Right, that's a partially positive carbon. It's more partially positive than the other site. So that's why the water is going to attack there. Sorry about that. So that site is more partially positive and is more apt to be a so that primary site is less positive. So the nucleophile is not going to attack that as readily. Right? All this little stuff like this goes on the back of the flashcard. These are reaction characteristics of this reaction that'll help you when you see it and you got to predict the product, or you got to answer a question about the regiochemistry, right? That's a characteristic dealing with the regiochemistry, right? And then the third question, so why are OH and Br on opposite sides? Right, that's the third question. Why is the OH and the Br, why are they written on opposite sides? Let me go back up here. I'm gonna copy that and paste it down here. What do you think? Somebody who was who logged in on Monday, you can chime in.
Is it said that they won't touch?
Yes, that's exactly right. What do we call it when they touch? What's the problem with them touching? What's the term I gave y'all for that on Monday?
Steric
Intermediate.
Steric interference. Good.
Yeah.
So you'll get if the OH and Br were on the same side, let me show you what that would look like. So you have the OH would be here. Sorry about that. Let me get this together. All right, so the product, if the product looked like this, where the OH was here and the Br was here, you got to think bromine is huge, El Gordo, right? Boom, and then you got the OH here. When those two groups are in proximity like that, that's going to be a problem, right? You're going to get what's called steric interference or steric hindrance. Right? Normally when you see this written like this, you'll see a little symbol that looks like that. That's telling you that when those two groups are going to clash, basically. And when that happens, the energy goes up. So they will much rather be apart from one another or opposite sides of one another than be on the same side, right? So that's another characteristic of your halohydrin as well as the halogenation reaction, is that the product is always trans, right? The bromine and whatever the other group is going to be trans.
Question.
Go ahead.
Since you said the energy goes up with the model that has the steric hindrance, you would say that the first one is favors, like equilibrium favors.
Yes.
The first one.
Yes.
Okay.
Great observation. If they were in equilibrium and in competition with one another, the product that's shown here is going to be favored over the product that's shown here, where the two groups are cis. That's exactly right. That's a great observation.
Okay, thank you.
Good question. All right, any questions? So that's, again, the reaction. You have it. You have the product. Where is it? Up here somewhere. Yeah, so you got the overall reaction you have right here. Right, that's your reaction. That's on the front of your flashcard, along with the title. On the back of the flashcard, if you can fit the mechanism, by all means do it. If not, at least put the characteristics. That is always trans, that the O8, that the water is going to attack the more substituted carbon. That's the other part of that. And then, what else did I say? So the regiochemistry, the more substituted carbon, it's the stereochemistry being trans, and then the water is going to attack that more substituted site, not the other bromine that you lost, because of the concentration of water is so much higher. All right. Any questions about anything that we just seen? And again, hopefully you are not watching the videos, because what we're doing now is basically reinforcing what you've seen in those videos. Maybe with some more details and some more information, but you gotta prepare. This is a section where you can't come in without stretching. You gotta stretch before you come in and work out with this. Otherwise, you're gonna pull something. All right, let's go up to some of the other examples, and then we're gonna move on to another reaction. We're gonna do, I think I'll have enough time to do hydroboration. Let me tell you about this reaction right here. Right, this is also halohydrin formation. Can somebody predict the product for that reaction? If it's a halohydrin, it's the same as this, right? So same outcome. The NBS is just a different bromine source. Let me write that somewhere. I'll write it. Let me erase that. MBS, I'm gonna show you what that looks like. It's a different source of our bromine. That's what MBS looks like. Does all that fancy smancy stuff is fine, but this is all I care about. It's giving me a bromine, right? So what do you think? What's the outcome? Where's the OH going to end up? Where's the bromine going to end up?
The OH, is it going to be on the more substituted?
Absolutely. Right? We just saw that in the other reaction, right? So now, if we know it's a halohydrogen synthesis, then we know the outcome. There's going to be an alcohol on one of the carbons in the double bond. There's going to be a bromine on the other one, and they're going to be on opposite sides of one another, right? So let me draw the product, and then you can tell me if I'm right or wrong. Sometimes I'm wrong. And so on this side, that's what my bromine is going. Come on, stop lagging. I'm going to slap these folks around here digging up these cables. They keep screwing up my internet. All right, is that okay? Somebody's thinking. I know somebody's asking this question. Well, where's the double bond? When you react that alkene, that double bond does not exist anymore. The electrons in the pi bond get used at some point in the reaction. So you no longer have a double bond in the product. Any questions about that? No question.
Why is there extra bond where the Br is?
It's not extra. You see, there's a, right here, you see this is CH3?
Yes.
It's the same. That's
okay.
The same CH3 that's bonded to that other carbon in the double bond. I just moved it down so I can show that these two are on opposite sides.
Okay, I see.
I could have drawn it this way now. Don't get the, let me show you. I could have done it this way, where I put the OH up here and the Br down here. But either way, that CH3 group is still gonna be there.
Okay, I see it.
Yeah, I'm just gonna put or, because it really is all semantical. It doesn't matter which, as long as you draw the OH and the Br on opposite sides, it doesn't matter. All right, let's go down here to these. I'm gonna do a couple of those eliminations, and then we're gonna move on. We only got 8 minutes though. All right, so the question asks, what alkene? What is that telling you? What's an alkene again? Oh, I'm retired next week.
A double bond.
Something, a compound that contains a double bond. So you go, so what this is asking you, it says which alkene can be used to prepare each alkyl halide. How do I get an alkyl halide from an alkene? I'm working backwards. This is what we call retrosynthesis, right? I have, look at what I have. All of these are alkyl halides. Everything down here is alkyl halide. So I'm trying to work backwards to get back to the alkene, right? So the alkyl halide is the product. The alkene is the starting material, right? The way that we make alkyl halides from alkenes, we got two methods. We can add Hx or add X2. Follow? To the alkene. That's what we just did in that very first example. That's a way to make alkyl halides. And I think I showed you that when we first started talking about these reactions too. All right, so let's take the, which one do you want to do? Once you do one, the rest of them you'll be able to do. And let me see if I can buy somebody lunch today. All right, if you're trying to get back to the alkene from the product, what type of reaction do you need to do? Lunch is on the line. When I add HX to the alkene, what type of reaction is that?
Halogenation. Hold on.
You're in the ballpark. Okay, so what's the generic type of reaction? If I take a double bond and I react it with HX, in the generic sense, what did I do? I only got 4 types of reactions that we've learned so far, right?
Addition.
Yeah, electrophilic addition.
Addition. Okay. So if I'm trying to go backwards, what's the reverse of addition?
Elimination. Subtraction, yeah.
Ooh, subtraction. When did we talk about subtraction? I'm about to throw something through my camera. I don't know who it's going to hit, but it's going to hit somebody. It's elimination, right? Addition. I think I told you that when we first started, when we talked about the 4 different types of reactions. Elimination and addition are reverses of one another. I heard somebody say elimination though. Who was that?
It was me.
Don't lie now.
It was me, but he said subtraction, so I was like, yeah, that sounds better.
That sounds better. We ain't never talked about subtraction.
I know, but I was like, well, maybe that is right, but I did say elimination.
Okay, so I owe you lunch. It's elimination. There's no, we never talked about subtraction. I get it though, because you're right. Addition, subtraction, in the regular world, yes, but in chemistry, addition and elimination are reverses of each other. So we need to eliminate. That's how we're going to get from the alkyl halide back to the alkenes. We need to do an elimination. All right. So let's take this one for instance. The first one right here. So the way I work backwards to go back to the alkyl halide is I find the halogen. I find the hydrogen next door. Anybody remember what those are called? Come on. Screen is frozen. Man. Anybody remember? When you do an elimination, what the hydrogens adjacent to your leaving group are called? If they wore black and gold, anybody remember that? I should have put lunch on that question. The alpha hydrogens. Right, so the elimination part we'll do here. We're just gonna put the arrows in.
Oh, I see what you did there when you said black and gold.
I'm trying to help you, but y'all didn't take it. I didn't take the rope. I tried to throw you a rope, but you didn't take it. So we're going here, boom, and here, right? So what we would get from that would be an alkene that looked like this, plus what? HBr. It's that simple. So all these questions ask you to do the same thing, work backwards. So my suggestion, find the leaving group and find all the alpha hydrogens, right? You got one here in this case, and then you got hydrogens here as well as here. So you can start with 3 different alkenes in that case. All right. What about,
Wait, I have a question.
go ahead.
How come you reacted the H and the Br together? Like, could you not have just left like one H still on?
Oh, it's still there. Yeah, yeah. You're talking about right here?
Mm-hmm.
Yeah, there's one. There is one still there. I only took off one of them.
You took off one.
Mm-hmm.
Oh, okay. Okay.
Remember, you gotta have 4 bonds. And then there's also one here, but that's not alpha, right? But it's still there in the product, well, in the start material. So if I took these two and reacted them together, that should get me back to here. That's all that question is asking. So working backwards, we call that retrosynthesis, where we take the product and work our way back to the starting material. All right, we got to stop because it's 11:59, and on homecoming week, I always stop 1 minute early.
Wow, a whole minute. Thank you.
A whole minute early. You should be grateful that I'm not talking until 12:10. Now, any questions? Anybody got any questions? I know this was a lot. Please, 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 I can't stress enough. Go and watch the videos that I sent. Look at the syllabus. Read those sections in the chapter. I promise you, it's not going to click in 40 minutes or 50 minutes while we just sitting here chewing the fat. You got to do some stretching. I see you, Caleb. So on Friday, when we come back, we're going to go to, I need you to watch those videos on hydroboration, oxidation, and oxymercuration. That's going to be the topic for Friday. We're going to look at a bunch of examples on Friday and get this handout, download it somewhere, put it in your phone so you can annotate it, however you want to do it. But you got to come strapped. You can't just show up. All right, any questions about anything? No questions?
Not right now.
All right. Well, that's good. Or it can be bad, but I'm going to take it as being good. All right. So I will see y'all on Friday.
Thank you, Dr. Russell.
All right. Take care. Have a good day.
You too.
All right. Stop recording. And I'll post all this stuff to Blackboard shortly.